lecture 9. Today I am going to talk about what is an integral domain and then I will form the quotient field. So, let us start. I have already introduced the notion of zero divisors previously. So, today we will say that there is a ring which have some properties where we do not have any zero divisors. These rings are called integral domain. So, let us start with the definition of integral domain. So, let R be a ring. So, an integral domain R is a non-zero ring which does not have any zero divisor. So, it is a integral domain is nothing but a non-zero ring having no zero divisor. So, what do I mean by zero divisor, that you already know. So, having no zero divisor means that if the product is of two elements is 0. So, if suppose A B is 0, then it should imply that either A is equal to 0 or B equal to 0. So, that means that there should not be any elements, any two non-zero elements such that their product is 0 element. So, if a ring has this property that whenever you consider two elements and take their product, if that product is 0, then one of them has to be 0. So, for example, in the ring of integers, if you consider, if you multiply two integer non-zero integer, it can never be the 0 integer. So, that means integral, an example of integral domain is nothing but the ring of integers. So, apart from that, there are many examples. Let us first see some of the examples. So, Z is an integral domain as we do not have any zero divisor in Z. And apart from Z, if I consider the polynomial ring over a field X, so where F is a field. So, this polynomial ring over a field is in fact an integral domain, because if you multiply two non-zero polynomials, then their product can never be the 0 polynomials. So, this is a field, then this is an integral domain. But in general, if I consider any ring R and consider the polynomial ring over that ring R, is it always integral domain? Not necessarily. So, the remark that I would like to make is the following, that if R is an integral domain and you consider, if R is an integral domain and you consider the polynomial ring over R, that means the polynomial ring over R in indeterminate x, then this is an integral domain. But if R is not an integral domain, in that case R x need not be an integral domain. We will see some of the examples later. Apart from this, we also have this example of field, any field if you consider. So, any field is an integral domain. In fact, we have seen that in any field all the non-zero elements have multiplicative inverse. So, they are units and units can never be a 0 divisor. So, if you consider any field, then it is certainly an integral domain. Now, I will give you one example which is not an integral domain. So, let us consider the ring of all continuous functions from R to R. So, this is what the set of all continuous functions from R to R. So, from real numbers to real numbers, the collection of all continuous functions. So, F is continuous. So, if I consider this set, then we have already seen that this has a ring structure with pointwise addition and pointwise multiplication. So, is it possible that two non-zero continuous function can multiply and give me the 0 function? We will see example that yes, it is possible. So, this is not an integral domain. So, for example, so note that this is not an integral domain. So, why is that? So, let me give you two functions, non-zero functions such that their product is giving you the 0 function. So, let us consider the function f x defined as f x is equal to x for all x greater than equal to 0 and 0 for all x strictly less than 0. So, this is one function, and consider another function g x. So, this f x is a non-zero function and g x I am considering the function g x to be 0 for all x strictly greater than 0 and x for all x less than equal to 0. So, if you consider these two function and then if you see what is how does this looks like. So, if you see that then if I draw the graph of this function, then you can see that suppose the function f is nothing but for the negative it is 0 and then from here it is x, and g function suppose let me denote it by this. So, g function is for positive x it is 0 and for negative x it is greater than equal to sorry for this one is this. So, now if you see that product of these two function if you consider, then this is nothing but their product is 0. So, here you can check that here f into g is identically 0 function, but neither f is equal to 0 nor g is equal to 0. So, therefore, this is not an integral domain. Apart from this, I will give you one more example. So, let us call the previous example as example 1, which is not an integral domain. Now, consider the next example. So, for example, we know that Z quotient NZ is a ring. So, let us specifically consider Z quotient 6Z. So, Z quotient 6Z if you see, then this is not an integral domain, because in that case 6 I can write it as, so this 2 bar into 3 bar is equal to 0 bar, but none of this 2 bar or 3 bar is equal to 0. So, we have this 0 divisor 2 and 3. So, here 2 bar is not 0 and 3 bar is not 0. So, we can see that in general if I would like to comment, then Z quotient NZ will be an integral domain if and only if n is a prime number, because so let me put it as a proposition also. So, Z quotient NZ is an integral domain, Z quotient NZ is an integral domain if and only if n is a prime number, because you already know if n is prime, then Z quotient NZ is in fact a field and every field is an integral domain, and if n is a composite number, in that case I can write this n bar which is nothing but the 0 bar as product of two non-zero elements. So, in that case it will not be an integral domain. So, Z quotient NZ is integral domain if and only if n is a prime number. Now, we will see there are some nice properties of integral domain which is known as the cancellation property. So, what is that? So, let R be an integral domain. Now, if the product of two elements A B is same as A C and A is not equal to 0, then what I can do? I can cancel from both side A, and these will imply that B will be equal to C. So, this is only true, that means I can cancel only it is in a we are in a integral domain. So, let us see the proof of this. So, I am having that A B equal to A C. So, this I can rewrite as A into B minus C equal to 0. Now, since R is an integral domain and A is non-zero, so that will imply that B minus C is 0. So, since R is an integral domain and A is non-zero, this implies that b minus c has to be equal to 0, which says that b equal to c. So, in general we cannot cancel this element a from both sides, but if it is an integral domain, then using the property of integral domain, this cancellation property holds. So, it is a very special to integral domain. So, integral domain has a nice structure because we can cancel out, and two non-zero elements can get multiplied and never give you the 0 element. So, now we will see another property of integral domains, but integral domains need not be filled, that we have already seen, because it may not have 0 divisors, but not every element have multiplicative inverse. For example, Z is an example which is an integral domain, but it is not a field. But if I impose some condition on integral domain, then it can be a field, and one of the condition is that if you consider a finite integral domain, then it is in fact a field. So, let me state that first. So, so a finite integral domain is a field. So, we will prove that if you consider a finite integral domain, then every element has multiplicative inverse. So, let us try to prove this. So, I need to show that every non-zero element has a multiplicative inverse. So, let x be a non-zero element in the integral domain, and then if I consider so I basically wants to show that x has a multiplicative inverse. Then we will be done, we will be able to prove that in that case every element I have started with any non-zero element and it has inverse. So, it will become a field. So, in how to prove that it has multiplicative inverse. So, consider the set of elements x, x square, x cube and so on. Now, it will continue, but we are in a finite integral domain, that means all of these elements cannot be distinct. So, since the integral domain is finite, all of these elements cannot be distinct. All of the above elements are not distinct, that is that there exist some powers, say r and s, such that there exist r greater than equal to s, some integers such that x to the power r will be equal to x to the power s. For some powers it has to be equal, otherwise we can have infinitely many elements. So, this implies nothing but x to the power s, if I take out, then x to the power r minus s minus 1 is equal to 0. Now, here I will use the fact that it is an integral domain. So, since it is an integral domain and x is not 0, therefore, x to the power s is also not equal to 0, and product of these two element is 0, that will imply that x to the power r minus s is equal to 1, which is nothing but x into x to the power r minus s minus 1 equal to 1. So, from here I can see that the inverse of x is nothing but x to the power r minus s minus 1. Therefore, this element x has a multiplicative inverse. This implies that x to the power r minus s minus 1 is the multiplicative inverse of x. Hence, every non-zero element has a inverse, therefore, it is a field. Hence, this integral domain is a field. Hence, the integral domain is a field. So, we have seen if you start with any finite integral domain, then it has to be a field. Now, next what we will do is that we will motivate you with this construction of rational numbers from the integers. So, already you know So, you start this, you know that this is not a field, but you can construct Q such that Z is sitting inside Q and this Q is a field. So, every integral domain, next what I am trying to prove is that if you start with any integral domain, then you can always construct a smallest field which will contain that integral domain, and that field has some special name which is known as the quotient field. So, the construction of this quotient field from any integral domain is exactly the same way as we have constructed Q from the integers. So, let us recall quickly how we have constructed this rational numbers from integers. So, if you see the how we constructed the rational numbers. So, you can see that this rational number half is same as this rational number 2 by 4, which is same as the rational number 3 by 6 and so on. So, all these rational numbers that I am having is representing the same rational numbers. So, these rational numbers are nothing but can be viewed as equivalence classes if I define the equivalence relation properly. So, how do I define the equivalence relation? So, you can consider, so let me do it next. So, consider, so this is the construction of rationals from integers. I will recall these things quickly. So, let us consider the set Z cross Z minus 0. So, this is the set where the first coordinate is all the integers and the second coordinate I am having non-zero integers. So, now I am defining a relation on this. So, define a relation on this set by, so I am saying that A comma B is related to C comma D if AD minus BC is equal to 0. So, if you see that this is the same condition when I say that these two rational numbers are equal, that means half, say half is equal to 2 by 4, this is same as saying that 4 into 1 minus 2 into 2 is equal to 0. So, motivated by this construction, we have defined that A comma B is equivalent to C comma D if AD minus BC is equal to 0. Then you can observe that these rational numbers are nothing but the equivalence classes that I have, this rational number can be viewed as this equivalence classes. So, but for that I need to check that this relation that I have defined is a equivalence relation. So, note that this is an equivalence relation and these rational numbers are nothing but the equivalent classes under this equivalence relation. So, and I know that if we have a equivalence relation, then this set can be written as disjoint union of equivalence classes. So, then this Z cross Z minus 0 can be written as disjoint union of this equivalence classes, and these equivalence classes are nothing but the rational numbers. So, let us denote the equivalence class of this element A comma B by A by B. So, this is the notation A by B that we are familiar with when we represent a rational numbers. We always represent the rational numbers in the form A by B, where A is any integer and B is a non-zero integer. So, these are nothing but the equivalence class under this equivalence relation that you can observe by this property of the equivalence relation. It is defined in this way. So, this is, and then we can see that among these equivalence classes, that is nothing but the rational numbers, that is how we have these rational numbers are nothing but the equivalence classes, because if you consider the rational number half, then we can see this is an equivalence class, and not only this half is there, I can have say many other numbers. So, 2 by 4, 3 by 6, all these are representing the same equivalence class, which is I can say that equivalent rational number half, all these are the same rational numbers. So, now I can define this addition on this rational numbers. How I have defined? So, I have defined the addition of two equivalence classes. This is how you define the addition of two rational numbers. What we have done? We have said this is nothing but AD plus BC divided by BD. So, since B and is non-zero and D is also non-zero and Z is an integral domain, therefore, BD will be non-zero, and this AD plus BC is nothing but the addition that we are doing in the addition and multiplication that we are doing in the ring of integers. So, it is saying that this addition is defined in this way, and I have also defined the multiplication of two rational that you already know. So, how the multiplication is defined? It is defined as AC by BD. So, this equivalence class. So, since again R is an integral, so this ring of integers is an integral domain and B and D are non-zero, therefore, their product is non-zero, and this is the product we have considered in Z. Therefore, this product of these two equivalence classes is defined as this one, this equivalence class corresponding to AC comma BD, which I have denoted by this one. So, then you can see that with these two operation addition and multiplication, Q is in fact a ring. So, with these two operation that I have defined by plus, which is usually known as the addition, and dot, that is known as the multiplication, this Q is a ring. So, this Q is nothing but the equivalence classes. So, where Q is nothing but the equivalence classes. So, we have defined the addition and multiplication between the equivalence classes, and we are viewing the rational numbers as the equivalence relation defined on the set Z cross Z minus 0, and the equivalence relation is defined in this way. And not only that, you can see that in Q every element has a multiplicative inverse. So, in Q every element has a multiplicative inverse. What is the multiplicative inverse? So, if I consider say A by B is an element, so this is suppose non-zero element. So, this is not the 0 element. So, this implies what? That A is non-zero. So, then I can talk about, then I can consider the element B by A, because A is non-zero, then B by A into A by B is nothing but 1 by 1. That means that A by B has multiplicative inverse, which is B by A. So, every non-zero element in Q has a multiplicative inverse, therefore, Q is a field. So, Q is a field. So, we have seen the construction of rational numbers from integers via defining a equivalence relation on the set Z cross Z minus 0, and these rational numbers are nothing but the equivalence classes of this equivalence relation, and this is how I have defined the addition between two equivalence classes, and multiplication is defined in these two equivalence classes. And here the additive identity, which is nothing but the equivalence class corresponding to 0 by 1, and the multiplicative identity is nothing but the equivalence class corresponding to 1 by 1. So, with all these things we have seen that Q is forming a field. So, Q is the smallest field that contains this integers, and I can view these integers as the elements of this Z are sitting inside Q via this map. So, what is that map? Let me say. So, you can see that I can identify the elements of Z as elements of Q via this map phi. So, phi of any element n, I am considering it to sending the corresponding equivalence class n by 1. So, we have we can view Z, we can view Z as a subring of Q via the above map. Fine. So, here we have identified the elements of Z as sitting inside Q via this map phi, where phi of n is we have mapped it to the equivalence class corresponding to n by 1. So, this is how we can identify that Z is sitting inside this field Q, and in fact, this Q is the smallest field which contains Z, and this Q has a special name which is also known as the quotient field of Z. So, I will next time I will define what is the quotient field and what will be the analogues of this construction of Q from Z, what will be the analog of this thing if you start with an integral domain and try to construct a field out of that where it will be sitting inside. So, these are the references that I have used for this today's lecture. Thank you.